Let me just introduce Avi here. Avi Goldfarb is going to speak today about the impact of AI on prediction versus judgment. This is a topic that's getting a lot of attention lately, and he and his co-authors have given a lot of thought to it. He's a professor over at the Rotman School, NBR Fellow, and Chief Data Scientist at the Creative Destruction Lab up in Toronto. So welcome, Avi.
Thank you. Just have to wait until you figure out if that's worth it. So this is work with Ajay and Joshua, and I'm going to proceed in two steps. So my first 20 minutes is going to be what's usually our general interest talk. It depends on how interrupt. You guys know that. So it might end up being 30 or 40 minutes. And then at the back, we're going to try and formalize it in the parts where the general interest talk is a little unsatisfying. Okay? So let's start with thinking about Moore's Law. Right? So when you think about Moore's Law, what's Moore's Law really about? What's changed? It's really a change in the cost of arithmetic. Right? So if you think about what this dramatic change in the speed of processors are, when you think about the economics of it, it's arithmetic is less expensive than it used to be. Okay? And it turns out there's all sorts of applications for arithmetic that we didn't dream of when arithmetic was so expensive that humans had to do it, that become incredible opportunities when all of us do it. So, we start with things like the Manhattan Project, right? So that was clearly an arithmetic problem. We understood that. Accounting, that's an arithmetic problem. But then it turns out, once arithmetic got sufficiently inexpensive in the 70s, we started to see games and mail and pictures and music and the internet. These, turns out, when arithmetic is inexpensive enough, we use arithmetic more for all sorts of things that we just didn't realize were arithmetic problems. Okay? So that's where we're going to start. Then we think about in 1995, in 1995 we had what everybody besides economists called the new economy, right? And we had this idea that the world was changing, economic rules didn't really apply anymore, but as economists, we realized, well, actually, economics is kind of the same. All this changes, there's some fundamental changes in the cost of certain inputs. So search was less expensive. The marginal cost of production of digital products was essentially zero. These products were non-rival. And it turned out that we had a whole bunch of good economic models for thinking about these things. And so you think about Shapiro and Varian's information rules book is just saying, look, it's not a new economy. The cost of a couple inputs have changed. And given that, we can understand, we have sort of years and years of literature for understanding these ideas. Now let's jump to 2016, and suddenly everybody's talking about AI. So what is it? And we had the White House just in December talking about their the Obama White House, the artificial intelligence automation of the economy, why deep learning is suddenly changing your life. And so we have this same idea. We have the technology. We have something, there was some kink around 2012 where suddenly whatever this is has gotten a lot cheaper. Okay? This is something we just see everywhere. And what is it? We're going to argue, or we argue, that it is the cost of prediction. We call it artificial intelligence, but the current generation of artificial intelligence technologies aren't some abstract artificial intelligence. It is a very particular set of technologies around machine prediction, taking information you have to fill in information you don't have. Okay? So there we go. A little brief history of AI. According to the Oxford English Dictionary, it's the theory and development of computer systems able to perform tasks normally requiring human intelligence. Okay? Now, there's a little bit tautological in there because normally is pre the technology, and then post the technology doesn't anymore. In the 60s and 70s, AI was rule-based. So it was very much symbolic logic. This is good for factories. This is good for chess. If this, then this. A whole bunch. So AI programs were essentially lists of if-then statements. And then it turned out the world was pretty complex, and those lists didn't work in all sorts of contexts. And so Markov calls this the AI winter, where in the 1980s we just kind of gave up. In fact, everyone gave up, but a couple of researchers in Canada. And then in the 2000s, that research became valuable again in the sense that we had this idea that we can program computers to learn from example data or experience. So we don't need rules-based. We don't really need to know what they're supposed to do. The current generation of AI is, let's just take a whole bunch of input data, figure out what we supervise, what the outputs are, and try and use a new set of inputs to predict a new output. Okay? So as Hinton said, you take any old problem where you need to predict something and you have a lot of data, and deep learning is probably going to make it work better than any of the existing techniques. Okay? So Hinton is one of the founders of this particular AI technology called deep learning. Almost all of AI's recent progress is through one type. So we call it AI, but it's really something very specific. It's some input data A is used to quickly generate some simple response B. Right? So for those of you who are thinking AI is scary, maybe it is in some abstract way, and maybe it is way down the road. But right now, this is what it is. It's prediction. Okay, so why prediction? Prediction is the ability to take information, take known information to generate new information. That's how we're going to define prediction. Yes, it could be about the future, because that's something you don't know. That's the new information, but it could be about the present. Right? So in Target's famous example of identifying which of their customers were pregnant, they weren't predicting the future, they were predicting the present or the past, from your point of view. And it's knowing, they just had an unknown piece of information, whether this person was pregnant, they were predicting that. Okay? And for those of you who've scanned through a standard machine learning textbook, how many were at MIT, so a bunch of you will be in this space. It looks like an econometrics textbook with a couple extra techniques and some different symbols. Okay, so the idea is maximum likelihood estimation, Bayesian, multivariate, linear, PCA, clustering, nonparametric regression. These are things that we have been teaching in econometrics or teaching in undergrad stats for years. There's a few new techniques or new edge like regression trees, neural networks, and Markov models, but the basic ideas are things that we should be very familiar with. And the methods themselves aren't really new. Even neural networks is an old method. I remember dealing with it in grad school about 20 years ago. I just kind of gave up on it because it was really, really slow in the computers I had at the time. It's not so slow anymore. The technology has advanced. The computer speed has advanced. The data collection technology, the data storage technologies have advanced. And the algorithms themselves behind neural networks have gotten better. And that means that there's now better prediction techniques than we used to have. Okay? Just to be clear, Ajay, Joshua, and I take no stance on whether prediction is truly intelligence or not. Okay? Jeff Hawkins thinks it very much is the essence of intelligence. Other people think it has nothing to do with intelligence. From my point of view on the economics, I don't care. Okay? So I just want to put that out there. I'm calling it artificial intelligence because that's what other people call it. It is prediction technology, a reduction in the cost of prediction. Okay. So now I'm going to do the intuitive version, which came out most thoroughly in the Sloan Management Review article. But the 800-word version showed up on HBR blogs. And so here's the idea. Advance in AI is a drop in the cost of prediction. What does that mean? We're going to do more predictions. Okay? Simple economics. We're going to do more predictions. Okay? Just like, well, when you move from film cameras to digital, just like when you move from film cameras to digital cameras, we're going to take more pictures. We're going to use less chemicals. Okay? We're going to see this prediction technology first in things like loan defaults. And that's an old prediction problem, really old prediction problem. It turns out machine learning is good at it. So we're going to see that in loan defaults. Then we're going to see it in things like predicting customer characteristics, targeted advertising, the target pregnancy example. Then, okay, medical diagnosis. That may not obviously be a prediction problem at an intuitive level, but if you think about it, it is. We don't know what disease a person has, so we're using data to predict what disease that person has. Diagnosis is a prediction problem. So we're going to see, as prediction becomes cheaper, we're seeing it in diagnosis. Object classification. You don't think, okay, I see an apple, and that's an apple. You might not think of that as a prediction problem. And for all I know, that's not how your mind operates and how it works. But for the computer, it's a prediction problem. It has an object. It doesn't know what it is. That's the missing information. It uses data from past objects that have been input into it. and says, ah, that's an apple. It fills in the missing data. So object classification turns out to be a prediction problem. And then there's all sorts of other things that we might never have dreamed of being prediction problems, like autonomous vehicles. Okay? Well, how is that a prediction problem? Well, at the high level, it's not, except what you're doing is predicting what a good human driver would do. Okay? So once we have enough data, it's a prediction problem if we can train it with enough, with enough data. So autonomous vehicles, one of the core insights in the resurgence of autonomous vehicles today, or the not resurgence, but the arrival of autonomous vehicles today, is this insight that all we need to do is predict what a good human driver would do. If we can do that, then we can transform this problem of driving into a prediction problem. Okay. So we see more prediction. Now, the other thing that happens is the value of other inputs changes. So we're still sort of in Econ 101, right? We see more prediction, or more machine prediction. Just like with fewer chemicals, more software, we're going to see less human prediction. Okay? So if we have more machine prediction, we're going to have less human prediction. Not that sort of straight substitutes. And so what you can think about is a model or a structure where you want to take an action. Okay? Humans want to take an action. To simplify it, you have data coming in. The data generates a prediction. To take the action, you need a prediction and you need some judgment. We're going to leave the definition of judgment loose for now, and I'm going to try and sharpen it once we get to the formalization. So to take an action, you need a prediction, what's going to happen, and a judgment, maybe the consequences of that action. In terms of how much you care, how much you value different people's utility, that sort of thing. That's going to generate an outcome, and then there's a feedback loop. So if machines are doing more of this, humans are going to be doing less of this. But in the way this is structured, at a high level, judgment is a complement to prediction. You need both to create an action. So if we're going to have way more predictions, machine predictions, we're going to see more human judgment. So we're going to end up with more judgment, and that's what humans are good at, and less human prediction. Okay? So human prediction is less valuable, human judgment is more valuable. Okay, so let's take a step back. I've said judgment, and I've waved my hands, and I'm going to kind of continue to wave my hands for a little bit. But what's judgment? Judgment is the ability to make considered predictions, or considered decisions, okay? In the intuitive version, so it's the version so far, judgment is anything that's not prediction or data. A little unsatisfying, but the way you look at this, okay, anything that goes into an action that's not prediction or data is judgment, okay? So what could that be? That could be ethics. Maybe, at least at first, we can't train the computer to do the ethics. Knowledge of utility functions. Maybe you can't really know the utility functions until you know the state of the world. So the prediction isn't going to be useful. You also need, on top of that, some knowledge about the utility functions given the state of the world. That's how we're going to formalize it today. Task definition. What is it that should be predicted? How do we think about, how do we separate these things out? What data goes in? All of these are, in principle, at least at first, judgment problems. Emotional intelligence, knowing how people are going to react to certain things and communicating could be a judgment at this point. Yeah?
Can't you cast a bunch of those?
Eventually, right? So that's the autonomous vehicle problem, right? So once you have enough data, then any of these, in principle, could become, our line between prediction and judgment could move. Okay? So that's why we're going to need a little formalization. But that is yes, that is exactly why, as I fully admitted, I'm handling it. Yeah.
So it's part of the problem that artificial intelligence, because we continue learning, replicability is going to be very hard. And then judgment and replicability have to go together, right? I'm going to be able to do better judgment if I believe that I can replicate whatever the artificial intelligence did. So I trust better the inference that I do.
So I think that's a separate. So we have the way we model is essentially there's a task, and there's data coming in, and that generates prediction, And then the data is imperfect in some way, and so you sort of add on top the judgments. You're saying there's a feedback loop, and it's a dynamic problem. And it's a dynamic problem in a few ways. So one way that it's a dynamic problem is so over time, if you see enough judgments, it becomes prediction. So autonomous driving it used to be a judgment problem, now it's a prediction problem because we see they follow thousands of miles. And that's going to essentially move, essentially you can think about that as reduction of the particular cost of that kind of prediction. And a judgment where judgment remains is in the on the rare event side.
Wouldn't judgment be about desirable versus undesirable states? That is what you are considering. So it's a state as an outcome, so it goes with prediction?
Perhaps. Okay. But the challenge with that is, let's say I observe millions of people judge stuff.
Right.
Okay? Now I can predict what the next person is going to judge. And so the judgment becomes a prediction problem. And
actually, I'm going to stick with your autonomous vehicle. Yeah. I can crash into the school bus or I can crash into the ambulance.
Right. But if it sees millions of people choose to crash into the ambulance,
that's okay. So you redefine it as a wisdom of crowds.
Well, that would be that's
utilitarian.
That's a utilitarian. But the other way is to do it by
yeah. I mean, if I'm going to one location and Michael's going to a different location, you don't want the car to go to the average location that people go to. I mean, it's not going to be very useful to me. I mean, however many data points, you want to know where I specifically want to go, right?
I thought your original definition of judgment was very elegant. Is any decision that a machine cannot make. That's
right.
So that's called resolve.
It covers it all. A lot of people find it unsatisfying,
No,
but that's where we are.
That's because the definition of artificial intelligence used to be whatever human can make.
It's like artificial intelligence is anything the machine cannot yet do. And once it does, it is computing.
Okay.
It's true. It's very important that the evolutionary step.
Right. No, I'm sympathetic to that point of view. That's where we are. That's absolutely where we are. Yeah, exactly. So that's where we are. And so there are. Let me say there's. Okay. So yes, I agree. Let's start there. Two points. One is once we get to formalizing, we can think about it in a variety of ways. So one, and the way I'm going to go is to say, until the state of the world is known, so you predict the state of the world, until the state of the world is known, it's hard to know what the payoffs are. You can get some surprises on payoffs to really understand utility, and that's going to be, we're going to essentially say, knowing the utility function is judgment. Okay? And then we're going to formalize that and think through the consequences. An alternative way to think about this that we haven't quite figured out how to get around is to say prediction is about understanding the non-parametric mapping between independent and dependent variables. Okay? Judgment is knowing the data generating process, the underlying model, that can sometimes improve that mapping between X and Y. Not always, but sometimes. And so when there's missing data. So that we haven't quite gotten our heads around. You disagree?
Yeah, I disagree. Yeah. I mean, I find it hard to think about, forget the autonomous vehicles, that's not good. Think about, something that's happened for the last 10 years, and that's replacing radiologists with computers. So you do an MRI or you do a scan and you want to know whether there's a tumor, right? And machines can do that very well now, better than many radiologists can. Now, what's the utility function? There are issues of type 1, type 2 error and all of that. What's the task? Those are things that go into the prediction. You make the prediction using all of that. The ethical judgment, should you allow a machine to detect cancer or it has to be a live doctor? I mean, that goes into the prediction. It's not something separate from the prediction. All of those things are things that define the predictive test.
No, but that set of definitions is what we're going to, are complements the prediction.
It's not complement. The prediction is meaningless if you don't have a a very clear picture of exactly what it is you're trying
So
to do.
let's think through the radiologist. So the radiologist, so patient comes in and their arm hurts, okay? So task number one is to figure out, is there a need for some kind of a scan, okay? Task number two is then identifying the particular scan that they need. Task number three is conducting the scan. Task number four is then doing the scan and figuring out if there's a break. Task number five is then explaining to the patient, or in terms of radiologists, more likely the GP, how do you interpret this probabilistic sense of whether there's a break? Because at the end of the day, these scans are probabilistic, whether they're interpreted by a radiologist or not. And then so how do you sort of communicate the idea, and then what's the action that you should take? The last part is in terms of treatment. Okay? So in terms of radiology, the machines are overwhelmingly getting better than humans at is there a break?
Not the machine, it's looking at the scan and being able to interpret the scan.
Right. But there's a decision in the background, which we're going to call a judgment decision on what do you scan. And there is also a task around, and talking to radiologists, a lot of radiologists view what they are really good at is explaining to GPs who are terrible statisticians what it means that this person has a 67% chance of this kind of cancer, a 20% chance of that kind of cancer. So the prediction is these numbers. And then there's a interpretation task.
You're taking something and adding, we can also talk about how do you make the patient feel happy and, cut time, reduce the time in the waiting room and all. You're adding a lot of things. But the basic prediction task is you've got a scan. Somebody decided that you're going to do a scan. Is there a break or tumor or whatever or not? With deciding how you compare type 1 versus type 2 errors.
Yeah.
That's the job.
No. So I see where you're coming from, but I'm going to say that, as you pointed out right away, that alone, just knowing, okay, the prediction task alone isn't useful without the other tasks that go with it. Just knowing if there's a tumor or not doesn't tell you anything unless you've already decided to do the scan and had some sense of how to interpret it afterwards.
Unless the patient had lunch, she's going to starve. I mean, there are all kinds of things.
No, but
I think this is very particular to that.
So, I mean, the machines can very easily distinguish an apple from an orange, a dog from a cat, a tumor from a not tumor. The machine doesn't care. It's the same algorithm. It does all those things. But I think what Avi's saying is that someone has to say, okay, you know what? Apples versus oranges maybe isn't that valuable today, but tumor versus not tumor is important. So we're going to take this amazing technology, and here's a set of things that we decide to apply it to. That is the deciding what to apply it to. The machine can't do that on its own. So there's at least one task, and there's, I think, others that you need to also do separately from just running this algorithm on just pointing it at random things in the universe.
I agree. There's one thing though that I meant, the language thing does concern me here, because if we're talking about a tumor, I would argue, and most people who do machine learning in this would argue, that's a classification problem. You're not predicting whether it's a tumor, you're classifying it. A prediction is about a future state.
No. So the definition of prediction we're using is taking information you have to fill in information you don't have. Classification is just that the structures are latent.
Time is irrelevant to you in this definition.
In terms of the prediction.
Got it. Good, fine. That's fine.
Mathematically, the time doesn't really matter either. Yeah.
It's a label thing. I mean,
that's fine.
I think you could call this all classification problems.
We could call them all classification.
Yeah,
well,
but
no.
And then say we don't have a label for.
Yeah.
No, predictions about a future state, assigning a probability to a future state.
So statistical prediction is generally, you can do statistical prediction about the future. When we think about the word prediction in statistical context,
right,
it's often about the present or even the past.
Right.
Yeah.
Let me ask you something that comes up all the time with AI, which is accountability.
Okay.
So in medical decisions, when a human makes it, we assume the human is accountable. If the machine is making it, it gets much less clear whether there is somebody accountable, there could be a bug, not the right data.
Yeah.
And so the reason I think we almost always, maybe always, want a human to make the final decision may come down to accountability. So is that a correct way to think about it?
I would argue that this structure allows you to think through all sorts of problems like that. So that is, okay, so accountability, there's two parts to that. One is, but fundamentally, I think it's about the legal system. And how does the legal system treat essentially delegated authority to the machine, where you say, okay, you can do, if the prediction is this, that happens, and the prediction is this, that happens, versus a check where a human says, gets the prediction and makes some kind of change to what the machine says. And then, if we have time, there's another step, which is that, in principle, a human can say yes, no, but always essentially listens to the machine. In which case, maybe the legal context is taken care of, but effectively the machine still has real authority. Real authority, in the sense that if the human just trusts the machine, always goes with what the machine says, and we're gonna.
No, I understand.
Yeah.
The reason it's an interesting problem is, at some level, you could say that's true of all engineering.
Yeah.
That if you don't use CAD/CAM tools to design the building, then you're doing something bad because you're not using the best technology.
Yeah.
If you just use the CAD/CAM tools and you don't have civil engineers and whatever finalizing the decision, that's also wrong. And we've set up a whole system for dealing with this, and this is the latest manifestation of that evolution of
Right, but there's going to be,
engineering.
yeah, no, I agree, but there's certain things that now we might not need a human in the loop for, or at least the loop becomes bigger, or we have to redefine what the loop is, which I think is was an earlier point. Yeah.
But one of the things we see happening in the field is that people are taking steps up the ladder. So you say, oh, I don't know what your utility function is. You say, well, maybe I'll watch people and I'll look and see if they're smiling, and they'll try and infer the utility function, and now that becomes a prediction button. Yeah. Because they'll move up. And so, I mean, I think a lot of these programs are a question of, is there a level?
Is there a limit?
You can't
So, yeah, okay, so this isn't, we thought about this. This isn't so much, it's not in here, but there's a few constraints on the limit, okay? Constraint number one on the limit is the extent that people care about privacy, okay? So if, the limit requires machines to get trained by data, anything that humans are unwilling to give to machines, and for some reason, and are still able to create that constraint, that creates a limit on what goes there. Relatedly, is going to be, that's going to require some legal framework around that. Another thing is some events are just rare, right? And so for truly rare events, it's going to be hard to get the machine to predict well, because it needs the input of data. Right now, maybe the predictions are going to get better. It doesn't need millions of observations, but for true rare events, and presidential elections are a good example of this. Right? They only happen once every 4 years. And the world changes in those 4 years. So that becomes a very hard problem. It's another potential limit to the machine. The third limit to the machine is, in certain situations, humans might want to sabotage the machine. Okay, so machines might want to trick each other, but also it might be that, look, if you're training a machine to replace your job, you might not want to do it very well. Okay, and if you have some unique skills, if you don't have unique skills, then you're at a loss. But if you have some unique skills, that's another potential limit. Yeah.
So the last thing you brought up, isn't that solvable with contracting of certain types? Like, you're not going to replace yourself, but someone else can get paid to replace you.
It's sort of an empirical question in each particular context and whether the value is higher.
Sure.
Yeah.
So I would argue that on all 3 points, you have another technology which is the complement, cryptocurrencies and blockchain, which gives you privacy, and you can do the prediction without exposing the data. And you can aggregate utility preferences in real time by a crowd to do a vote, or make a decision in a rare event situation.
Okay.
An edge case.
So this is something we should talk about later, but my My quick response is that's under a particular set of assumptions about aggregation of preferences. And if that set of assumptions is wrong, then that won't be true. Yes.
Question, I think you mentioned self-reference, like Gödel's theorem of self-reference machine. Is that really considered as nothing? Like, is that within the kind of machine you mentioned? You mentioned that.
What do you mean?
So like the Gödel's theorem that there is one that it's not possible for a machine to there's one equation in the machine will never be able to solve which says it's sort of like it's self-referencing equation.
I'm happy to add another one.
In any context that it requires that knowing the answer, true or false value of that equation.
Okay.
Not be able to.
Yeah, I worry that that's a pretty small set, but sure.
Well, I mean,
Yeah.
I'm asking you, it is a small set. I mean, if that's true, then the machine eventually decides to set that one.
Well, no, I think the other constraints I just put forward are all limits. Okay. So let's formalize this now a little bit. Okay. So let's say there's a safe action with payoff S. There's a risky action with payoff R, small r cap I. Okay? The high payoff is bigger than the safe payoff, is bigger than the risky payoff, is bigger than the low payoff. But in this particular structure, if you don't have a prediction, you're going to take the safe payoff. Okay? Essentially, you can flip this around, and most of what will follow will just flip over. But for now, let's. This, I think, is the most intuitive way to structure. So we're going to say, if you don't,
It's
in the
a 50-50 chance of the two states.
50-50 chance of the two states, and in the absence of prediction, you're going to take the safe action. With perfect prediction, you're going to end up taking the safe action half the time when your prediction tells you it's the state with small r, the low state, and you're going to take the risky action the other half of the time. It's no longer risky because you know you're going to get the high. Okay? Now, what is prediction? We're going to start by modeling prediction as some probability the decision maker learns the true state. Okay? We will later flip it around to think about it as a guess at a prediction with some likelihood that the prediction is true. But it turns out the results go either way, and the math is easier here. So we're going to have, in this case, with a prediction, our payoff is going to be that probability times the high, what we're going to get in the high outcome, or sorry, what we're going to get with prediction, minus what we're going to get in the safe. Okay, so what this is going to tell us, okay, better prediction leads to a higher payoff, not surprising. And the returns to that prediction are going to depend on the difference between the payoff in the good state, if you take the risky action, relative to the safe action. Safe action. Yep.
When you learn the truth, is the probability that you're going to know what it is to find out ahead of time?
Yes.
You wasn't able to predict?
Yes.
Okay. Yeah. That's why I thought you found out you couldn't, as opposed to you thought it could, but gave you the wrong prediction. No,
it's in advance. Okay, it was a good word. We can do it. I'm going to add the other kind on later. And so we're going to specify judgment in a very, very particular way, which is that the decision maker can't describe the utility function perfectly in advance. So it can't tell the machine, this is the utility function. But once the state of the world is known, once you get the prediction, the decision maker assesses the payoff from each action. Okay? So the payoffs in these previous slides are now your prior beliefs. And judgment is the ability to recognize these hidden attributes when they arise. Okay? And what those hidden attributes are is either a cost or an opportunity. So first, let's start with and we're going to do this all symmetrically, so things work out nicely. So with probability rho over 2, the decision maker learns that the risky payoff in the good state is actually a little better than they thought. Okay, that's called a hidden opportunity. With probability equivalently rho over 2, the decision maker learns that the risky payoff in the good state is less than they thought, minus that. Okay? And then with some probability, 1 minus rho, that is actually what they thought. It's all. Okay? And so with some regularity conditions, what we're going to get is the opportunity is going to lead to a risky action under uncertainty. And the cost is going to lead to the safe action under certainty, even more so. Okay? Now, we were going to do the safe action essentially. So we're going to have some probability of getting good news or bad news. Okay, so a couple more parameters. And so in the absence of any prediction technology, we've got this ugly payoff. Okay? But what this ugly payoff means is if there's, in the absence of prediction, if there's no hidden attributes, we do the safe action, just like before. Right? There's nothing's really been added here. So in the absence of hidden attributes, that's what we had before. No hidden attributes, we do the safe action. If there's a hidden opportunity, now we might do the risky action, even when there's no prediction. And this means that sometimes now, unlike before, we could do the risky action and end up in the bad state and get small r. It wasn't possible before now, but this extra delta means it's possible that under certain parameter values, we're going to end up with a risky action in a bad state. But the hidden cost under no prediction, we're still going to be doing the safe action. So it's irrelevant, no impact. So what does that mean? It means judgment is going to be useful. So just think this through. Judgment is going to be useful when it changes the action. So in the intuition I had up front, I said, look, we have judgment and we have prediction and they're complements. And at least one of you said, wait, this, I don't like that for a variety of reasons. But now, once we formalize it in this particular way, actually it turns out sometimes they're substitutes and sometimes they're complements. It actually just depends on whether the prediction, whether the judgment is actually going to change the action relative to what would have happened with the prediction law. Okay? And without prediction, only good news changes the decision from the safe default. And prediction doesn't change it back. So this good news, hidden opportunities turn out to be a substitute for prediction. So in the way we've modeled right now, the positive news is a substitute for a good prediction. In contrast, bad news changes the decision. In the bad news model, okay, we were going to do safe. The prediction tells us to do risky. And then, wait, we get new information about the utility function that moves us back to safe. Now we have that the new information changed the decision and it becomes useful. Otherwise, it has no real value. Okay? And maybe this is obvious now, but before we worked through it, we didn't realize that this is 30-year-old math at some level. And so if this is a bad news principle, this is real options theory as applied to prediction and judgment. So we can, and actually that insight, we're going to be building on that, which is the idea that once we think about this as a prediction problem, we have dozens of years of good economics work on thinking about asymmetric information that give us sort of a myriad of opportunities to think about the consequences of AI.
So I think I missed one. So it says without prediction, only good news. Prediction does not change it back, right?
Yeah.
And so am I missing something? Because if you don't have prediction, you take the risk, and sometimes you're lucky, and it was high R, and sometimes you're unlucky, and it's low R. So without prediction, you sometimes risk having a bad outcome. With prediction, you would never take the action if it was low R, right? Small R.
Yeah.
So isn't that a change? It says it does change.
It doesn't change your action.
It does change your action. You're not going. Then you're going to play the. If the prediction says small r, then you're going to play the safe option, aren't you?
No, but so if the prediction says
that the
small
true
r,
state is small r, yeah.
You'll do safe.
Right, and that's
Okay.
different than what you would have done without the prediction.
No, because with that, you would never.
Without the prediction, you're going to gamble.
No, but Without
without prediction, in a good state of the world, you're going to gamble.
without the prediction, you're gonna gamble.
Right.
With the prediction, you're gonna gamble, but it's
Not-
not gambling.
Not
Not
if
if
it's
the row is-
not if R is small. That you play it safe.
Oh, yeah. Okay, so that's this. Sorry, we sort of assume that. That's okay. Yeah.
This is actually judgment. It's still just
So, yeah, no, that's right.
or the prediction, no prediction, you're calculating.
So we are saying that judgment is the knowledge of payoffs after the prediction is made. That's how we define it. It's related to our original definition of judgment is the stuff that you can't predict. And here is a particular thing that is unpredictable.
Do you find out something you predicted and now it's called judgment?
That, yes, and that seems to be how, you don't like that, I think. But that's, when we think about, so we, the stuff that, so we've defined sort of in the background, the stuff that you can't predict is judgment, okay? And the technology, look, the technology is improving over time, so we can think about the threshold of what you can predict is changing over time. And here is a particular way to say, here is one thing, we have the prediction is good up to a point, and then there's some error in the prediction.
So this should be isomorphic with Bayes. Bayes. You have priors, you have posts. Probabilities. Row is the probability. You have the prior, you have the post. You should be able to reformulate this in Bayes. That's what Bayes does. You have evidence. You have a certain.
So, to the extent that, you know,
and it
log
turns out to be,
is
it turns
the
out to be
version
the
of,
red ball.
of that,
the white
then
ball.
yeah, right.
Okay.
But so as long as there's stuff you don't know at prediction time, right, and then new information comes in,
Right. That's updating.
And that-
updating. Your
that
new
updates-
information update. So
and you change your behavior.
So
Yeah.
some graduate student is going to reformulate what you've done into a Bayes. There's going to be some sort of transform that turns into Bayes.
Sounds great to me.
So I've been thinking about this event as being a coin flip, but I think to turn it into a judgment story, it's not you're predicting a coin flip, you're predicting whether George is going to say yes or no. And now it's judgment because I'm predicting what George is. Is that why this extra piece is judgment?
No, you're predicting whether it's going to rain or be sunny. That's the prediction. And then the judgment is when you go outside, how important is it to you to have an umbrella at that moment?
So that's already factored into the decision.
So it's somehow that wasn't the best, but the way we model it is to think through until you're out there, and I know your mental state at that particular time. I don't really know how much you care about opening your umbrella. There's new information that comes up, and when you go outside, you look, and you say, "Oh, it's raining." That affects your decision. So the prediction is about the state of the world. The way we model the prediction is about the state of the world, and the judgment is about the utility from different actions in the different states of the world. Make sense? Not really? Okay.
So, I don't know, you're focusing on individuals in your examples, but maybe it's better to think about the firm. So,
Okay.
So the idea would be, let's say you're Facebook and you have a prediction of how much policy change is going to affect engagement versus messaging with other users.
Yeah.
But then, how much you weigh the two in your decision problem, which algorithm launch is the judgment problem, and that would be asymmetric to the views about chaos. Is that?
Yeah, so the way I think about Facebook, so maybe this is the same thing we just said. Maybe it's not. So let me try it, which is that, look, Facebook's newsfeed has historically been optimized on engagement. Okay? That decision to optimize on engagement was a decision that doesn't, actually that's not this model, so maybe that's not the right way to think about it. That's another judgment problem, which is that maybe optimizing on engagement led us to the wrong macro outcome for Facebook as a whole, even though once you optimize engagement, the prediction problem is quite straightforward. Okay. So I don't have a good answer.
Well, yeah, show an ad. And
Yes.
the ad, there's a chance that they click on it, and the payoffs, depending on what the payoffs are, you may want to just always show the ad, or you may want to wait and have a prediction as to whether they're going to click on the ad. I think that would be a way of describing what you have there. And so, well, most ads don't have a 50% click rate, but,
But you can, you can sort of rescale everything to be at that point one. Okay. So radiology.
here we go.
So in our conference last year said, we should stop training radiologists now. Okay. And he went on to say, we have lots of radiologists. Maybe this won't be solved in a year, but in 10 years, it's pretty clear that that the machines will do image recognition. Like, oh, there's something, object recognition. Oh, there's a mass there, better than humans. Okay? So that led me to go out and interview some radiologists. Okay? And so what did radiologists say? They said, well, yeah, the machines do this really well. And this is where my response was, which is that, but here's where I spend my time. I spend my time on figuring out what kind of scan to do. And I spend my time, once I have the outcome, actually the most of my time is then communicating to these GPs who have terrible stats. What do they do with that information? Okay? And so there's some sense that maybe the training and expertise required of radiologists will be different in the future, but that role of expertise in interpreting images may remain. Okay? But what does this mean in our particular context? So the safe action is the biopsy. This is a little bit of perhaps unintuitive, but the safe action is the biopsy. It's invasive, identifies infections. Okay? The risky action is wait and see if more things develop. Okay? Radiology is a non-invasive method that allows doctors to take the risky action. Okay? So it gives you some ability to say, you know what, let's wait and see. Okay? Better radiological prediction is going to lead to fewer invasive exams. That's sort of the prediction number one that comes out of the model before we add. And so as prediction improves, there's going to be less need for judgment of the kind, let's get a biopsy when prediction says wait and see. Like that's the option. But when invasive procedure is recommended by prediction, we might get human judgment choosing to wait. That's sort of thinking through if you believe these two things, then this follows from the model. Yeah?
These are optimal decision problems. Passive control theory. Control decision problems.
They're decision problems where you have, I don't mean to be saying that a theory is radical and new. I mean to be saying that in those decision problems we have data that allows us to predict a piece, and we have an uncertainty piece. And what we've layered on here is that uncertainty piece. There's things that the machine, that aren't uncertain to the decision maker, that are uncertain to the machine. And so we have that distinction. And then as the stuff that the machine can do gets better, that changes that human part to it. Yes, I do not mean to say that the mathematical model itself is radically new. Okay. So. Got 5 minutes left? Ish?
5, 10, yeah.
Okay. So a couple extensions. So what if the prediction is wrong? Okay. So this is, in addition to our, we know for sure that we have a good prediction. We're also going to have, we know for sure that there's some that we have a prediction, but there's some probability that we do know in advance the prediction isn't actually right. That probability is going to be A. We're going to assume this is going to be independent from the stuff. And the prediction is good enough so that when you have the prediction, you're going to take the risky action. That's our constraint that we're going to operate with. First point is that doesn't change anything. So our quality, this idea of, as prediction improves, we're going to see we're going to see more judgments of a certain kind and less judgments of the other kind. It's still going to hold here. And to be honest, if we did A first, then E, and only did the A, we would get the same result. That's just what makes it a little more interesting is let's now have some model where we trade off the the ability to predict, E, with the quality of the prediction, how good that prediction is, A. And so when we have it so that more predictions, if we do more predictions, those predictions are worse. That's sort of the trade-off. Then we're going to have a result where when the hidden costs are more likely, wait, let's just jump. No, okay. It's supposed to be a proposition. So the hidden costs, when R is low, so when things are, when the payoff to the good state isn't that high, we're going to want more prediction that's less reliable. Okay, so the decision theory is we're going to be wanting to know for sure that we're in the R state. We're going to want the prediction even if it's not that good. In contrast, when R is high, we have no clear static. When the risk is really high, so when the payoff is really high, there's no clear relationship between.
Ex ante.
Yeah.
What is the distribution between R is low and R is high? What is our expectation? What is our going in? What is our subjective expected utility?
Oh, so this is we know R. Okay? We know R, and this is under situations where R is low versus under situations where R is high. So the last result is real machine equivalent. Okay? So this is the idea. Look, for a given individual, there's lots of decisions you have to make. Okay? Some of those decisions can be predicted by the machine. So let's say all of those in principle, you're going to get a prediction. This is what you should do from the machine. And so the question is, when do you delegate to the machine and just say, okay, whatever the machine says I'll do, versus where will you look at the prediction, which is going to cost time and effort, and then decide whether to go with what the machine said. So this is related to your earlier point. So in the baseline, we're going to go back to the baseline model, so we're only going to have one uncertainty moving around. And we're going to have lots of environments, each with a different delta, which is each with a different sort of value of judgment. Okay, so we're going to have high opportunities versus the opportunity and cost of that delta, and it's going to be, well, sometimes judgment really doesn't do that much, and sometimes judgment does a lot. Okay, so, and they're going to have some cost to monitor. Okay, so,
but this is what this gentleman said. You have reconstituted that as a principal-agent problem. That's a principal agent. The machine is your agent,
yes,
and you are the principal.
Yes, absolutely.
Okay,
yes.
fine.
Yes. Yes. We are now in a principal agent problem. It's a little bit of an unusual principal agent problem because the agent has no reason to lie to you.
Sure.
But it's a principal agent
Depends
problem.
on the data set, but yeah.
Okay.
There's incentive alignment.
Yeah, there is incentive alignment. Well said. So what's going to happen is we're going to get, so obviously we're going to get judgment in states with hidden costs. Okay, so so just as before, we're going to use judgment in cases where where there's where we have the complements and not the substitutes. And the human's going to cede authority first, obviously, in situations where the machine is where judgment doesn't matter that much. Okay, that's the unsurprising result. What gets a little interesting is that there's going to be situations where the human is better at the decision, where the judgment actually adds value, that the human still won't listen. The human will say, they won't put the effort. The human's going to say, look, I'm going to do whatever the machine does, even though if I looked, I could make a better decision than the machine. Okay? And the reason that happens, and that's this kink, that's this jump here. The reason that happens is the marginal benefit of judgment is sometimes going to be, the marginal benefit of increased prediction is going to have impact over here, inframarginally, more than on the human-machine board. So what's going to happen is human judgment is going to require monitoring over lots of environments. If judgment becomes worse, the greater the span of control, then you're going to get these situations where, oh, it's actually going to help. It's going to shift this in a way that that value of judgment is high is where there's going to be the biggest boost, even paying more attention. And so some of the things in the margin you won't pay any attention to. And so you are going to cede authority to the machine, in principle, even though you're probably better than the machine. And then that creates some interesting legal ideas on who's liable for that kind of decision. If you know, hey, if you looked, you can make a better decision than the machine, but you choose not to look because your time is limited and you're focused over here, then that's another layer on top. Okay. And then as the prediction technology improves, we're going to get more machine authority. So as prediction technology improves, we're going to get, this is going to shift. We're going to do more things with the machine, but we can actually end up in situations where this jump becomes even bigger. Okay, so prediction gets better. So we're going to do more. We're going to give more to the machine, but when we judge, we really focus and we spend more time on it. Okay. What? So that's going to be because they're okay. So essentially, we have limited attention. We decided not to focus over here, so that attention is going to end up. So we can now spend more time over here, and that's going to be
Very good better predictions. Why not devote your limited attention to cases where you have bad predictions, where you have nothing to do?
Yes, that's sorry.
You have the other way around. You're saying that it's better to devote more attention.
So as prediction gets better, we're going to focus more attention to those things, to the things where judgment is still not.
So it's not that you're going to have more sources of judgment. It's just certain types of judgment you're going to do more.
So exactly. So we're going to spend more. We're going to be spending more time on an effort on the situations where judgment still, where judgment is particularly valued. Why did pi m go down? That is a better question for my co-author. Oh, because it's a cost. But I should have a better answer to you.
Oh, so those are costs, not benefits.
Yes. So, you know what? I didn't anticipate this. So, so I'm gonna kick that to.
Okay.
I will get back to you in particular, and ask Joshua. Okay. So, the high level point, I think, is that this is a useful framework to think about AI. Okay, it is a preliminary paper, and it suggests that so tautologically the thing left for humans is not prediction. Okay, we've labeled that judgment, but even in that situation, it's not quite as rosy as it seems because judgment's even there not always going to be a complement to prediction. It's going to depend on, sometimes it's going to be a complement, sometimes it's going to be a substitute, and the particular context of the example is going to matter. Okay? So, thank you.
All right, thank you. All right, well, thanks, Avi. So next, or 2 weeks from now, April 26th, we have John Van Reenen is going to be speaking here, and then May 3rd is Martin Goose. So we'll see you in a couple of weeks.